Welcome to White Space. Can the universe end in 3 different ways? And we still don't know which? Put this on in the background, close your eyes if you want, and let the story carry you. Most of us know space the way we know a foreign city from postcards. The broad strokes, the famous landmarks, a handful of numbers we half remember from school. But the universe doesn't reserve its most extraordinary features for the places that are easiest to see. The further you look, the stranger and more demanding the territory becomes. What lies beyond the comfortable boundaries of our solar system, and even beyond the edges of the galaxies themselves, is a story that our instruments are only just beginning to tell. This journey will take us through some of the most improbable landscapes in the known universe. We'll begin close to home, on a world where it rains liquid gas and the seas have no water. We'll spend time with the rocks that drift silently through our solar system, carrying catastrophe inside them. We'll visit the edge of our solar system, where a small, cold world turns out to be stranger than anyone predicted. We'll examine planets orbiting distant suns, where the conditions for life might not be entirely impossible. We'll pause at a system where something between a star and a galaxy is shooting matter across the sky at nearly a quarter of the speed of light. And then we'll step out altogether into the vast, nearly empty space between galaxies before asking the hardest question of all: how does the universe end? Saturn's moon Titan has a surface temperature of roughly negative 179 degrees Celsius. It orbits a gas giant more than 1 billion kilometers from the Sun. It has no liquid water anywhere on its surface, and yet of all the worlds in our solar system, Titan may be the one that feels most familiar from above. The reason is simple and startling. It rains there not water but liquid methane falling from orange hydrocarbon clouds, pooling into rivers and flowing down into seas. Titan is the only body in our solar system apart from Earth, where liquid sits openly on the surface and moves through a hydrological cycle. The liquid is different, the chemistry is different, but the landscape it creates is not detailed radar mapping by the Cassini spacecraft, which passed Titan more than 100 times between 2004 and 2017, revealed coastlines, river deltas, dunes and plains. The same physical processes that shape the surface of the Earth have been at work on Titan, substituting hydrocarbons for water at every step. The northern polar region hosts 3 major bodies of liquid. The largest, Kraken Mare, covers roughly 400,000 square kilometers and reaches depths of around 200 meters. Named for a sea monster of Norse mythology, it is wider than the Caspian Sea. Ligeia Mare, slightly smaller, sits nearby, while Punga Mare, the most northerly of the 3, is the most compact. All 3 are filled predominantly with liquid methane and ethane, gases so common in Titan's atmosphere that they condense and precipitate just as water vapor does on Earth. The equatorial regions are drier. Long, dark dune fields stretch for hundreds of kilometers there, shaped by the same slow atmospheric dynamics that create sand seas in Earth's deserts. The mountains are modest by planetary standards, but real. The craters are few. Titan's thick atmosphere and active erosion have buried or smoothed most of the evidence of past impacts, leaving a surface that looks geologically young and constantly remade. What sits beneath the surface may be equally remarkable. Analysis of how Titan's ice shell shifts relative to its interior suggests the presence of a global subsurface ocean, likely a mixture of water and ammonia, the ammonia acting as an antifreeze that keeps the water liquid at temperatures where pure water would long since have frozen solid. This ocean, estimated to lie roughly 100 kilometers below the crust, would be far too saline and chemically hostile to support any life we know. But its existence tells us that Titan is not a dead object. On the surface and in the atmosphere, the chemistry is genuinely complex. Titan's atmosphere is thick with nitrogen and laced with organic compounds, including one discovered only recently that had never before been found in a planetary atmosphere, cyclopropanolidine, a carbon-based molecule known from interstellar clouds and detectable on Earth only under laboratory conditions. Its presence on Titan suggests that the Moon's chemistry is rich and active enough to produce building blocks of greater molecular complexity. Whether those building blocks ever assembled into anything that could be called life is a question we cannot yet answer. Hypothetical organisms adapted to liquid methane rather than water, consuming hydrogen and exhaling methane instead of breathing oxygen and exhaling carbon dioxide would be radically unlike anything in our biology. They would require entirely different molecular machinery. Their existence, if real, would tell us something fundamental about the range of conditions under which chemistry can organize itself into something living. NASA's Dragonfly mission, a rotorcraft lander designed to fly between multiple sites on Titan's surface, is scheduled for launch in 2027. It will carry instruments capable of analyzing the chemical environment directly, searching for the signatures of prebiotic chemistry or something stranger. Whatever it finds, or does not find, will sharpen our understanding of what conditions are actually necessary for life to begin. The question of life elsewhere is one that human beings may spend many centuries answering, but its significance, if and when an answer arrives, would be difficult to overstate. The discovery of even a single organism unrelated to anything on Earth would transform our understanding of biology from the study of one example into a general science. It would tell us that life is not an accident unique to one warm, wet rock near an ordinary star, but a process that repeats wherever the conditions permit. That is a conclusion with implications no field of human knowledge would escape. Not all of what moves through our solar system is as remote or as alien as Titan. Some of it is much closer, and some of it is watching us without our knowing. On the 14th November 2020, a small asteroid designated 2020 VT4 passed the Earth at a distance of less than 400 kilometers, that is below the altitude of the International Space Station. The rock was roughly 10 meters across. Had it entered the atmosphere at the right angle, the energy released would have been comparable to the Hiroshima detonation. No one saw it coming until it was already past us. The fundamental problem with near-Earth asteroids is that most of them are small, dark, and fast. They absorb rather than reflect light. They travel across a sky that contains billions of background stars. A 50-meter object traveling at typical asteroid velocities carries enough kinetic energy on impact to level a mid-sized city, or, if it lands in open ocean, to generate a tsunami 10 meters or higher, capable of reaching coastlines hundreds of kilometers away. A kilometer-scale body would release energy measured in thousands of megatons across an impact zone the size of a continent. The shock wave would travel the circumference of the Earth. The debris thrown into the upper atmosphere would reduce sunlight globally, lowering temperatures and disrupting agriculture on timescales of years. The term extinction-level event is not an exaggeration. The Earth has been through this before. The mass extinction at the end of the Cretaceous period, roughly 66 million years ago, eliminated the non-avian dinosaurs and roughly 3/4 of all species then living. A larger body is thought to have struck the Earth at the boundary between the Permian and Triassic periods some 252 million years ago, killing an estimated 90% of marine species and 70% of land species. The planet recovered, but the time scale of recovery is measured in millions of years, long past any horizon that matters to a civilization. The Palermo scale assigns a numerical risk rating to known near-Earth objects based on their kinetic energy and the probability of an Earth-crossing trajectory. At present, no known object has a positive Palermo scale value, meaning none is judged to pose an imminent credible threat. 2 objects sit in the monitoring zone. The asteroid Bennu, about 500 meters in diameter, will make a close pass in 2035, approaching within roughly 300,000 kilometers, slightly inside the Moon's orbit. If the geometry of that encounter nudges Bennu onto a slightly different trajectory, subsequent passes could be dangerous. The OSIRIS-REx probe visited Bennu to collect surface samples and study its structure, data that would be essential for any future deflection attempt. The asteroid designated 1950 DA is the larger of the 2 monitored objects, at about 1.3 kilometers in diameter. Its mass may reach 4 billion tons. Its orbit intersects the Earth's, and the closest potentially hazardous approach is calculated for March 280. If that encounter were to result in an impact, the energy released would exceed 1,500 megatons. Every coastal city within reach of the impact site's ocean basin would be at risk from tsunamis reaching 40 meters or more. The dust load injected into the atmosphere would trigger temperature drops across the planet. The shock wave energy would be enough to reactivate dormant volcanic systems. The probability of 1950 DA actually striking the Earth remains below 0.02%, but the probability is not zero, and it changes as the asteroid's orbit is perturbed by gravitational interactions with other bodies. For a long time, all of this was simply observed and catalogued, because changing the trajectory of a mountain-sized rock traveling at 14 kilometers per second was beyond any technology available. That has begun to change. In 2018, NASA and SpaceX jointly approved the DART mission, designed to test kinetic deflection by colliding a spacecraft with the smaller component of the binary asteroid Didymos. The concept is straightforward. A small change in velocity applied far enough in advance can alter the orbital period enough to shift an asteroid's path away from an intersection with Earth. Even a change of a few minutes in orbital period accumulated over years can move a close approach from a collision to a safe pass. The margin of error in asteroid prediction spans decades. The window for intervention, if identified early enough, is measured in years. The challenge is detection. The solution is time. Some of the objects in our solar system are better known but no less surprising. Pluto, reclassified as a dwarf planet in 2006 and stripped of its 9th planet status, was for most of human astronomical history little more than a faint point of light, detectable only because it moved against the background stars. We knew its orbital period, its distance from the Sun, rough estimates of its size and composition. We knew almost nothing about what it actually looked like. The New Horizons spacecraft changed that completely. Launched in 2006, it reached Pluto in July 2015 after a journey of nearly 5 billion kilometers. What it found was a world of remarkable variety and unexpected youth. Pluto is primarily rock and ice, with a dense rocky core wrapped in an icy mantle, roughly 300 kilometers thick. Its surface is covered in frozen nitrogen, methane, and carbon monoxide, along with complex organic compounds called tholins that give it a reddish-brown tint. Its atmosphere is thin and composed mostly of nitrogen, with methane and carbon monoxide present in smaller quantities. The greenhouse effect from methane means temperatures in the upper atmosphere are actually warmer than at the surface, where they average around minus 223 degrees Celsius. The most striking feature, photographed by New Horizons, is Tombok Regio, informally called Pluto's heart, a vast, pale region roughly 1,800 kilometers across. Its western lobe, Sputnik Planitia, is a basin likely formed by an ancient impact and now filled with slowly circulating nitrogen ice. The surface there is geologically young, almost entirely free of impact craters. indicating that the ice is continuously renewed by convective processes driven from below. The eastern lobe is rougher terrain divided by mountain ranges of water ice rising as high as 3,500 meters above the surrounding plains. Right Mons, a structure 4 kilometers tall and 150 kilometers across, displays a summit depression and surrounding terrain almost devoid of impact craters. The most straightforward interpretation is that it is a cryovolcano erupting not lava but a slurry of volatile ices. If so, it would be the largest cryovolcanic structure known anywhere in the solar system. The source of heat needed to drive such activity is not fully understood. Pluto's rotation is retrograde, meaning it spins in the opposite direction to most planets in the solar system. Its orbit is chaotic in a technical sense. Observed over short timescales, it appears regular, but the trajectory shifts subtly with each pass until the original path is unrecoverable. A day on Pluto lasts 6.4 Earth days. A year lasts 248 Earth years. The 5 known moons, including the massive Charon, which is so large relative to Pluto that the two orbit their common center of gravity in space between them, form a system more complex than any simple description captures. New Horizons continues to operate. Moving outward through the Kuiper belt, it has passed the contact binary Arrokoth, formerly called Ultima Thule, and several other objects, while also reaching a position from which stellar parallax measurements can provide independent checks on distances to the nearest stars. The mission is expected to return data until at least 2026. The search for worlds that might support life has expanded dramatically beyond our solar system. For most of human history, whether other stars had planets was a matter of philosophical speculation rather than scientific inquiry. The first confirmed detection of planets orbiting another star came in 1992, when timing irregularities in the pulsar PSR 1257+12 were attributed to the gravitational influence of orbiting bodies. The first planet found around a Sun-like star followed in 1995, orbiting the star 51 Pegasi just 50 light-years away. Since then, the catalogue of confirmed exoplanets has grown past 4,000, distributed across more than 3,000 planetary systems. Statistical extrapolations from those numbers suggest the Milky Way alone may contain upward of 100 billion planets, with perhaps a fifth of them broadly similar in size and composition to Earth. Whether similar in size and composition means similar in the conditions needed for life is a separate and considerably harder question. Ross 108b sits 11 light-years from Earth in the constellation Virgo. It orbits a quiet red dwarf, a star significantly smaller and dimmer than our Sun, which means the habitable zone, the range of distances at which liquid water could exist on a planetary surface, is much closer in. Ross 108b completes its orbit in 10 days. But because its star emits so much less radiation than the Sun, that tight orbit still places the planet within the temperature range where water could theoretically remain liquid. Red dwarfs vary considerably in their activity levels. The ones that emit intense ultraviolet and X-ray flares represent a hazard to planetary atmospheres. Ross 120 is unusual in being a comparatively calm example of its class, which removes one major objection to its planet's habitability. Its mass is estimated at roughly 1.35 times that of Earth, a figure consistent with a rocky surface. Gliese 667c orbits a red dwarf within a triple star system 22.7 light-years from Earth in the constellation Scorpius. The two larger stars in the system are orange dwarfs, visible to the naked eye from Earth under dark skies. The planetary discovery was made using the Doppler method, detecting the slight wobble the planet's gravity imposes on its host star. The planet's mass is about 3.8 times that of Earth. Modeling suggests a mean surface temperature of roughly 27 degrees Celsius if greenhouse warming is comparable to Earth's own. Whether the atmosphere is actually dense enough or similar enough in composition to produce those conditions is unknown. The planet is almost certainly tidally locked, meaning one side permanently faces its star and the other is in permanent darkness, creating extreme temperature gradients between hemispheres whose effect on habitability remains debated. HD 855112b orbits an orange dwarf in the constellation Vela, 36 light-years away. Its star is older and less active than the Sun, having existed for more than 5.6 billion years without catastrophic flare events. The planet's mass is 3.6 times that of Earth, and it sits at the inner edge of its star's habitable zone. Liquid water on the surface would require a moderately high cloud cover to prevent runaway greenhouse warming, a condition that could plausibly be met but cannot be verified without direct atmospheric observation. The methods available for studying exoplanet atmospheres are still limited. Transit spectroscopy, in which the planet passes in front of its star and the starlight filtered through the atmosphere carries spectral signatures of its composition, has provided some data on the larger gas-dominated planets. For small rocky worlds at habitable zone distances, the signal is faint and the required observing time is substantial. The Cheops telescope, launched by the European Space Agency in late 2019, is specifically designed to refine measurements of known exoplanets, providing the precise size and density data needed to separate rocky worlds from sub-Neptune gas bodies. Future instruments will push further. Whether any of these planets harbor life in any form is a question that cannot be answered with current technology. The significance of the question and the pace at which our tools are improving suggests that it will not remain unanswerable indefinitely. In the constellation Aquila, approximately 18,000 light-years from Earth, there is an object that fits none of the convenient categories. It is called SS433, and it was first noticed in 1978, not because anyone was looking for it specifically, but because its radio and X-ray emissions were anomalous in a survey of supernova remnants. What further observation eventually revealed was a system of extraordinary violence and precision. SS433 is a microquasar, a compact binary system in which one component is likely a black hole and the other a massive star, roughly 10 to 30 times the mass of the Sun. The two orbit their common center of gravity every 13.1 days. As they do, material from the star flows toward the black hole and forms an accretion disk, compressing and heating to temperatures at which it emits X-rays. Some of that infalling material does not cross the event horizon. Instead, it is redirected into two narrow jets of plasma, ejected in opposite directions along the system's rotation axis at approximately 26% of the speed of light, roughly 79,000 kilometers per second. The jets themselves precess, rotating around the system's axis like a spinning top, gradually changing its orientation. This precession gives the jets a corkscrew shape visible across enormous distances. The diameter of each jet, measured at the distances where they interact with the surrounding nebula W50, is approximately 5,000 times the diameter of the solar system. W50 itself, the remnant of the supernova that likely created the compact object in the first place, has been distorted by the jets into an elongated structure that bears the informal name the Manatee Nebula. The details of SS433's jets were sharpened considerably by observations with the ALMA Observatory in 2019, which produced images of sufficient resolution to show the jet structure in detail. The images confirmed predictions made by earlier spectroscopic measurements using the Global Jet Watch network, which had modeled the jet geometry from Doppler shifts in the emission lines. Theory and observation agreed. The jets are narrow, knotty, and corkscrew-shaped. A regular quasar, by contrast, is an active galactic nucleus powered by a supermassive black hole with a mass potentially hundreds of millions of times that of the Sun. The luminosity of such objects can exceed the combined output of all stars in their host galaxies by orders of magnitude. The black hole at the center of SS 433 weighs only a few dozen solar masses, making it vastly smaller in scale. But the physical processes are analogous, and the relative proximity of SS 433 makes it possible to study those processes in detail that is simply not available for objects billions of light years away. The future of SS 433 is gradual. The regular star will eventually be stripped of its outer layers by the tidal forces of its compact companion, leaving a hot stellar remnant. The material transfer will continue until the star is consumed. The precessing jets will continue to carve through the surrounding nebula. On human timescales, the system will look much as it does now. On astronomical timescales, it is a system in transition, and the opportunity to watch that transition in real time is one that current and future radio and X-ray telescopes are well positioned to exploit. Beyond the last stars of any galaxy, the universe does not simply stop. It continues, but differently. Intergalactic space is not nothing. It is a thin, hot, ionized medium containing approximately 1 atom per cubic decimeter, 10 times less dense than the gas found between stars within a galaxy, but distributed across volumes so vast that its total mass likely exceeds the combined mass of all the stars and galaxies in the observable universe. The dominant component is hydrogen, ionized by the radiation from galaxies and quasars, but heavier elements are present too: carbon, oxygen, silicon, sulfur, and metals. These trace heavier elements were not produced in the intergalactic medium. They were expelled from stars by stellar winds and supernova explosions and carried out of their host galaxies into the spaces between them. The existence of this medium was not suspected until the 1960s, when quasars provided the first means of probing it. Light traveling from a distant quasar to Earth passes through enormous distances of intergalactic space, where that light encounters intervening gas. Specific wavelengths are absorbed, leaving gaps in the spectrum. Analysis of those gaps revealed the presence of the intergalactic medium before anyone had any direct way of seeing it. Since then, extended surveys have mapped vast filamentary structures in the distribution of intergalactic gas. The largest coherent structures in the universe, connecting galaxy clusters across hundreds of millions of light years, stars, exist in intergalactic space as well. They were discovered relatively recently, and their origin is the subject of ongoing investigation. Some are thought to have been ejected from galaxies by gravitational interactions, thrown outward during galaxy mergers or encounters with massive central black holes. Others may have formed in place within intergalactic gas clouds. Within the Milky Way's extended halo, hundreds of these runaway stars have been identified. Across the observable universe, the total number may reach several trillion. Many are detectable only in X-ray wavelengths, because they are members of binary systems in which the more massive component has become a black hole or neutron star, and the accretion of material from the remaining star generates a high-energy emission that ordinary optical telescopes cannot easily pick up. The dynamics of the intergalactic medium play a crucial role in the evolution of galaxies over cosmic time. Gas is drawn into galaxies by gravity at a rate comparable to the rate at which those galaxies form new stars, supplying the raw material for star formation continuously. At the same time, stellar winds and supernova explosions push material back out of galaxies into the surrounding medium, enriching it chemically and distributing the products of stellar nucleosynthesis across intergalactic space. Dead stars in any galaxy contribute their matter to a common reservoir. That matter eventually joins a different galaxy and becomes part of a new generation of stars. Nothing is permanently lost, it merely changes address. Understanding the detailed mechanics of this circulation has required simulation. Supercomputer models of gas dynamics on cosmological scales have tracked the movement of intergalactic matter over 13 billion years of simulated cosmic history, showing how gas flows along the cosmic web's filaments into the dense nodes where galaxy clusters form, and how outflows from galaxies propagate back into the surrounding medium. The models are not perfect, but they reproduce the observed large-scale structure of the universe with reasonable accuracy. Intergalactic space remains one of the least observed and least understood environments in the universe. It emits no visible light. Its density is too low to produce strong signals at most wavelengths. Its influence on the galaxies around it is real and substantial, but visible only through its effects rather than directly. Future observatories designed for radio wavelengths and X-ray astronomy may finally begin to map this environment in detail, tracing the flow of matter across the largest scales on which matter moves. Before any of that mapping is complete, the universe will have moved on, and in the very long run it will have ended. The question of how the universe will end begins with the question of what it is made of. The ordinary matter that composes everything observable, all the stars and planets and gas and dust and people, constitutes roughly 5% of the universe's total energy content. Dark matter, which interacts gravitationally but not electromagnetically, makes up about 27%. The remaining 68% is dark energy, a term that names a phenomenon while admitting almost total ignorance of its nature. Dark energy drives the accelerating expansion of the universe. How it behaves at very long time scales determines the universe's ultimate fate. The universe's expansion is already beyond the reach of our instruments in one direction. Sufficiently distant galaxies are receding from us faster than the speed of light due to the expansion of space itself, and no signal from them can ever reach us. The edge of the observable universe is not a physical barrier, but an informational one, defined by the distance light has had time to travel since the Big Bang. Beyond it, space almost certainly continues, containing more galaxies, but those galaxies have been causally disconnected from us since early in cosmic history. As expansion continues, the observable universe will gradually contract. Distant galaxies will redshift and fade. Eventually, the Milky Way's local group will be all that remains visible against an otherwise dark sky, and after enough time, even that will change. If dark energy remains at its current density indefinitely and expansion continues to accelerate, the Big Rip becomes possible. In this scenario, the expansion rate eventually grows strong enough to overcome the forces binding structures together. Galaxy clusters come apart first, then individual galaxies lose their coherence. Then stellar systems disintegrate as the expansion force exceeds gravitational attraction at smaller and smaller scales. Planetary orbits fail. The chemical bonds holding matter together are eventually overcome. Subatomic particles themselves are separated. The end point is a universe of freely dispersed elementary particles too thinly scattered to interact in a space that has grown without limit. If dark energy weakens, or if its nature is different from what current measurements suggest, and if the gravitational pull of all matter in the universe eventually slows and reverses the expansion, the big crunch awaits instead. In this scenario, the universe contracts. Galaxy clusters draw together. Galaxies merge the cosmic microwave background radiation, already cold to within a few degrees of absolute zero, begins to warm again as space shrinks. When the universe has contracted to a small fraction of its current size, radiation temperatures will exceed the threshold for liquid water. Life of any kind will be impossible. Further contraction continues until all matter is compressed into conditions resembling those of the original Big Bang, a hot, dense singularity in which the concepts of space and time as currently understood no longer apply. Some versions of this scenario append a further step, a new Big Bang, a new expansion, and a new universe. This is the Big Bounce, a cyclic model in which creation and collapse repeat on timescales that make the current age of the universe appear as a brief interval in an endless sequence. Neither scenario plays out on timescales that have any practical relevance to the Sun's lifespan or to Earth's habitability. The Sun has roughly 5 billion years of hydrogen-burning fuel remaining. As it ages, its luminosity will increase, and Earth's surface will become too hot for liquid water within approximately 1 billion years, long before the Sun reaches its red giant phase. The end of complex life on Earth, if nothing intervenes, is measured in billions of years. The end of the stelliferous era, during which stars form and burn hydrogen in the universe, is measured in trillions. The degenerate era that follows as white dwarfs and neutron stars cool and dark matter annihilation and proton decay gradually reduce the mass of residual objects spans scales expressed in powers of 10 so large that human language has no convenient names for them. The black hole era that follows will last still longer, as the most massive black holes slowly evaporate via Hawking radiation over timescales approaching 10 to the power of 100 years. After that, the universe is dark and cold, populated by photons, electrons, positrons, and neutrinos distributed at such extreme dilution that significant interactions become extraordinarily rare. What remains after that, or whether the word after is even meaningful in such conditions, is not something physics currently addresses with any confidence. What is certain is that the universe looked at from the beginning of one of its most productive eras is still in its early stages. The structures it has built, the galaxies and stars and planetary systems, are the products of processes that began nearly 14 billion years ago and have been running continuously since. The questions those structures raise about the origin of life, about the nature of dark matter and dark energy, about what lies beyond the observable boundary, about whether the universe that exists now is the first or the millionth, are questions that human beings have barely begun to formulate precisely enough to answer. Every new instrument extends the reach of that inquiry. Every new discovery revisits the context in which the previous ones are understood. The universe is not silent on these questions. It is simply answering them in languages we are still learning to read.